Welcome to part 4 of the GWN780x switches video guide series. In this video, we will focus on spanning tree protocol operation and configuration. We will explain how spanning tree protocol works and how it helps prevent bridging loops from happening over redundant links. Spanning tree protocol is a layer 2 protocol designed to prevent bridging loops in the network topology with redundant links between switches, like the one you see in this image. Basically, the main function of STP is to ensure that the network topology remains loop-free. Let's use this topology to help us understand the purpose of enabling spanning tree protocol on the switches. In this topology, we do not have redundant links, and the traffic forwarding seems to work fine. Computer C sends data to computer B, and the data arrives with no issues. However, a good network design does not only ensure traffic forwarding, but it should also consider how to recover from failures in a timely manner. For instance, if the link between switch 1 and switch 3 goes down, the devices connected to switch 3 will disconnect from the local area network, and a manual intervention will be required to restore the link. This is why it is always important to have redundant links in a network topology with multiple switches, so that a single link failure cannot interrupt the normal operation of a network. In this topology, if the link between switch 1 and switch 3 is down, switch 3 can still use the redundant link to send data to computer B. However, redundant links without enabling spanning tree protocol may also introduce switching loops that are undesirable. We will use this example where computer C sends a broadcast frame. Remember, switches must forward broadcast frames out all active ports in the same VLAN, except the ports that receive the frame. So when switches 1 and 2 receive the broadcast frame from switch 3, they will flood the broadcast frame out to all active ports, which results in retransmitting the same broadcast frame back to switch 3, and the broadcast loop just continues infinitely. The same thing can happen with unknown unicast traffic, which is a frame that arrives with a destination MAC address that is not found in the MAC address table of a switch. And in this case, the switch will simply flood the unknown unicast frame to all ports that belong to the same VLAN. So spanning tree protocol was particularly developed to prevent the risk of bridging loops by making the switches aware of the redundant links. It helps detect loops in the network topology and forces redundant links into standby state to prevent them from actively forwarding frames. So with STP enabled in this example, switch 3 will not forward the broadcast traffic on the redundant link, which is put in the blocking state. And the redundant link will be put in a forwarding state only if the active links fail or become disconnected. So now that we talked about the function of spanning tree protocol, which is to prevent loops in a network, let's explain how STP actually operates. For all switches in a network, to negotiate a loop-free topology, the switches must elect the root bridge, which will be at the top of the spanning tree. The bridge ID of a switch will determine which one will become the root bridge. Basically, the switch with the lowest bridge ID wins the root bridge election. The bridge ID is made of the bridge priority value and the MAC address. The default value for bridge priority on all GWN switches is 32,768. If all the switches in a network use the same bridge priority value, the switch with the lowest MAC address will be elected as the root bridge. You can influence the root bridge election by modifying the bridge priority of a switch. This is something that we can change from the web interface of the switch. In this example, we manually change the bridge priority of switch 1 to a lower value, which is 4096, to force it to become the root bridge. Switches exchange the bridge ID and other STP information using BPDU messages, and they use that information to agree on a common spanning tree protocol where the root bridge becomes the reference point for all other switches. After the root bridge is elected, configuration BPDUs are sent only by the root bridge, and all other switches will just relay them. If the other switches detect a change in the topology, they will send a topology change notification to the root bridge, and the root bridge will propagate that information to the other switches. Remember, in a spanning tree topology, most of the traffic goes through the root bridge. So to maintain an efficient topology, the placement of the root bridge must be predictable. The root bridge should be a distribution switch or a switch that is directly connected to the router. In this example, we should not use switch 2 or 3 as the root bridge because it makes sense to elect switch 1, which is directly connected to the router. So the next step after the root bridge election is to decide which links to use by the other switches to forward traffic to the root bridge. Switches use the concept of STP path cost to determine the best path to use to reach the root bridge. The root path cost is the cumulative cost of all links to the root bridge. The cost is determined by the link bandwidth. The higher the bandwidth, the lower the cost, and the more likely the link will be used to forward traffic. GWN switches support both short and long values for the path cost. It is critical that all switches in a spanning tree topology use the same value type. If you decide to use the long values, then you should apply it to all other switches to avoid unpredictable path cost calculations. So in this topology, both switches 2 and 3 will use their gigabit port 1 to forward traffic to the root bridge because these ports have a lower path cost, and they are directly connected to the root bridge. The redundant link, which has a higher cumulative cost, will be put in a standby state. The ports that are directly connected to the root bridge and have the lowest path cost are considered root ports, and every switch except the root bridge must elect one root port. The ports on the root bridge that connect to other switches are all designated ports. A designated port can also send and receive traffic to and from another STP segment. As shown here, the port that connects switch 3 to switch 4 will be a designated port because it will work as the forwarding port for that STP segment to and from the root bridge. For the network to complete its convergence and become loop-free, spanning tree protocol needs to define the state of the ports on the redundant link. Spanning tree protocol will elect one port to become the designated port and the other port will enter the blocking state. STP will decide the state of the port based on these conditions shown here. In this topology, both switches 2 and 3 happen to have the same path cost to the root bridge. So the state of the ports on the redundant link will be determined by the sender bridge ID. Bridge ID is made of the bridge priority and the MAC address. And in this example, switch 2 has the lower MAC address. So port gigabit 2 on switch 2 will become the designated port. And port gigabit 2 on switch 3 will enter the blocking state. So after we briefly explained how STP operates to make the network topology loop-free, now let's talk about the STP timers that you need to configure from the web interface of the switch. After the network convergence is complete, the bridge route will send configuration BPDUs which are relayed to every switch in the network. The hello timer determines the interval between configuration BPDUs that the root bridge sends, and the switches rely on these BPDUs to check if there is a change in the network topology. By default, the hello timer is set to 2 seconds. Max H timer is the duration that a switch stores a BPDU before it expires. If no BPDUs are received during the max H timer, the switch transitions the port to a non-forwarding state. Another STP timer that you can configure on the switch is the forward delay, which is the time spent in listening and learning states before transitioning to a forwarding state. To better understand the forward delay timer, let's review the STP states first. Before the STP convergence completes, the STP enabled ports go through several states before they start forwarding data traffic. On a port that has STP enabled, it starts in the blocking state to prevent any bridging loops from taking place. In this case, the port can only receive BPDU messages and it is not allowed to process data frames. When the switch detects that it needs to move to the forwarding state, the switch puts the port in the listening state, in which the port is allowed to send and receive BPDUs to actively participate in the spanning tree topology process. At this stage, the port is still not allowed to process data traffic. The port stays in this state for 15 seconds, which is the default forward delay timer. After that, the port moves into the learning state, in which the switch sends and receives BPDUs and starts learning MAC addresses to build the MAC address table. The port stays in this state for 15 seconds. As you might have noticed, the port spends 30 seconds in the listening and learning states before moving to the forwarding state, in which the port is allowed to send and receive data frames as well as build and maintain the MAC address table. Remember that a switch moves a port into the forwarding state only when it has the best path cost to the root bridge. Now we're going to log into the web interface of a GWN switch and demonstrate how to configure spanning tree protocol. So we will configure STP on 3 switches and add a redundant link. It is important that you always enable and configure STP before adding a redundant link. So first we're going to log into the switch that we're going to elect as the root bridge. And the spanning tree configuration is available under switching, spanning tree. By default, spanning tree is disabled on the switch. When spanning tree is disabled on the switch, you need to configure how the switch will handle received BPDU messages. You can choose either flood or drop. When flood is selected, the switch will basically forward received BPDU frames out all active ports. When drop is selected, the switch will simply drop any received BPDU message. So in our case, we need to enable spanning tree. So let's just enable it. And under the mode, we have 3 options: STP, RSTP, and MSTP. Today we will use STP as defined in the standard 8021D. In a future video, we'll explain the difference between STP, RSTP, and MSTP. So I'm going to go ahead and select STP for today's video. As I explained earlier, the path cost is the metric spanning tree protocol uses to measure the shortest and fastest path to the elected root bridge. The main difference is that the long path cost increases the range of high link speeds, such as 1 terabit per second or 10 terabits per second. In a network topology made of GWN switches only, you can use either one. Just make sure that all the switches use the same type. So I'm just going to leave it as a default set to short. By default, all GWN switches have a bridge priority value of 32,768. Bridge priority value, again, determines which switch can become the root bridge of an STP topology. The switch with the lowest bridge priority value will be elected as the root bridge. We can change the bridge priority to a lower or higher value to influence the election of the root bridge. Keep in mind that you can only use values that are multiples of 4096. We want this switch to become the root bridge, so we will change the bridge priority from the default one to 4096. The max hop setting determines the number of switches a BPDU traverses before it is discarded. We will talk more about this setting next time when we cover MSTP. By default, the hello timer is 2 seconds. This timer controls the sending interval between the configuration BPDU messages. So I'm just going to leave it as a default. The max age timer is used by the switch to decide whether a stored configuration BPDU has expired if the max age is exceeded. By default, the max age timer is 20 seconds. So in our example, since we only have 3 switches, I'm just going to change it to 10 seconds. Just make sure you change that same value on the other 2 switches. The forward delay time is the period the port spends on the listening and learning states. By default, it takes the port 50 seconds to transition back to the forwarding state if it detects link failure. The 50-second period includes 20 seconds for the default max age timer 15 seconds for the listening state, and 15 seconds for the learning state. So I'm just going to leave that one as a default, set to 15 seconds. So after applying the changes, you will notice that the bridge ID has changed from 32,768 to the current value that we have configured under bridge priority. We will come back to these settings after we complete our STP configuration on the other switches. Next, we go to port settings. This page displays the spanning tree configuration of each port. You can use this page to verify the spanning tree parameters and states of the port, such as the port status and port role. To make changes to a specific port, we click on the edit icon under the operations column. When you enable STP globally under global settings, it gets automatically enabled on all the ports. If you decide to disable STP on a port, you can use this option. You only disable STP on a port where you are certain a loop will never happen on that port. Each port has a priority value, which is 128 by default. Spanning tree is also used in a case where you have redundant links between two switches as shown in this image. STP can use the port priority value for the ports to decide which port must be put in the forwarding state. The port priority is only used to determine the STP state when the redundant links have the same bridge ID, route path cost, and sender bridge ID. So STP will prioritize the port with the lower value and put it in the forwarding state. So if we want to prioritize port 1 over port 2, then we can reduce this value, for example, to have 64. We've already talked about the path cost of an interface, which is automatically calculated by the switch based on the link type. If you want to influence the path cost, you can choose a value from 1 to 200 million, but I will just leave it as the default. The next option is the edge port. Remember, a port on a switch goes through the listening and learning states before it starts forwarding data traffic, and that takes 30 seconds by default. Edge port is a feature that allows the port to immediately enter the forwarding state as soon as the link comes up. You should enable this feature only on ports where bridging loops are not expected, such as on ports that provide access to endpoint devices like computers and servers. So we know by now that spanning tree hinges on the exchange of BPDU messages to dynamically form a loop-free STP topology. The other feature that you can enable with edge port when you set it to enabled is BPDU guard. BPDU guard is a security feature that prevents receiving BPDU messages on interfaces where a BPDU is not expected. It also protects from rogue switches that might connect to the network and assume the role of the root bridge. So if a BPDU guard enabled port receives a BPDU message, that port is immediately shut down and the network administrator must manually re-enable the port if auto recovery is not configured and their port auto recovery configuration page. We will take a look at this setting in a moment. So it is strongly recommended to use BPDU guard on ports that have edge port enabled. So when you set edge port to enabled, just make sure you set BPDU guard as well. And of course, you should not enable BPDU guard on ports that actively participate in the STP topology. For example, if we are using gigabit port 1 to connect to another switch, then we should not enable edge port and we should not enable BPDU guard either, because we want the switch to receive and process the BPDU messages. So in a situation where you need to prevent BPDU messages from being sent or processed on specific ports, you can enable BPDU filter to exclude these ports from participating in a spanning tree operations. It basically forces the port to always remain in the forwarding state. This is why it is important to enable it only on interfaces where BPDU messages are never expected, such as a port that is directly connected to a server. So in the STP topology we're trying to configure, Gigabit Ethernet port on the root bridge will be used to connect to another switch. So in this case, we should not enable edge port, BPDU guard, or BPDU filter but we can enable these settings on another port that is used by an endpoint device. So after you enable BPDU guard, if a switch detects that there is a BPDU on a port that is not supposed to receive BPDU messages, the switch will shut the port down, and you need to go to port auto recovery. You will see that entry under the shutdown reason, so this way you know why the port was shut down. You can go under the operations column to force the recovery of the port. So let me go back here again to spanning tree. So now that we configured the root bridge, we changed the bridge priority so we can force it to become the root bridge. I'm going to go ahead and log into the other two switches and enable STP. All I need to do on the other switches is enable STP, set the mode to STP because all of them must use the same mode. And I will also change the max agent time to reduce the time it takes the switch to move into the forwarding state. Alright, so I went ahead and I logged into the web interface of switch 2 and switch 3, and as you can see, I enabled spanning tree protocol, I set the mode to STP, and I changed the max agent time to 10 on both of them. If we go back to switch number 2, here is the bridge ID of this switch, and here is the root bridge ID. Here it shows which interface is connected to the root bridge, which is switch 1. Since we are using the short values for path costs, so gigabit interface has a path cost of 4. It also tells you how many changes happened in the topology. So here it's showing 4, and when was the last change in the topology. If you go to the switch number 3, we're pretty much going to have the same settings. So this is the root bridge ID. This is the bridge ID of this switch, and the interface gigabit Ethernet 1 is the one that is directly connected to the root bridge. The path cost is 4, and the number of changes in the topology is 1. If we go under port settings, since we have two links that connect to the root bridge, the one that is directly connected to the root bridge is in the forwarding state, and the redundant link that we added to switch number 3 is in the blocking state. So you can refer to the port setting configuration page to monitor the status of the port. If we go to switch number 2 and the port settings, you will see that gigabit Ethernet port is the root port because it's directly connected to the root bridge, and gigabit Ethernet 2 is in the forwarding state and has a designated port role. So this concludes today's video guide about STP on GWN780x switches. In a future video, we're going to cover MSTP and RSTP. Thank you for watching, and I hope to see you in the next video guide.